Thanks for coming, everyone. For the E-Trax soil collection rover, our sponsor is Jeff Peterson. He's a private agronomist from Watertown, South Dakota. Something unique about our project is we have a semi-functional prototype that we have to optimize. I'm Josh Lamb. I'm a mechanical engineer.
Cody Kramer. I'm the Ag Engineering program.
Landon Noschel, Ag and Biosystems Engineering.
Brandon Kellenberger, Mechanical Engineering.
Seth Kepi, Mechanical Engineering.
So this is our overall project goal statement. We were given a prototype, as you saw on that title slide, that's basically a frame with some of the subsystems involved, and we have to optimize it to drive to a GPS waypoint and take a soil sample that's 24 inches deep within plus or minus 1 inch. And then it needs to collect at least 16 volumetric ounces, and then it needs to drive to another site that's selected, do the same thing, and needs to complete that 10 times. The 24 inch samples plus or minus 1 inch at 10 different GPS waypoints.
So this video here shows our current operating system that we were given. It is a carousel cup system with an auger drill bit. So the carousel will rotate, it'll flip a limit switch there, which will tell the auger and the cup grabber, which is at the base of the cup, to slide over on a linear rail system. It will then put the auger or screw the auger down through the cup. It'll then all pull it out together, and the cup grabber will go down to the soil where another limit switch will be flipped, saying that it is at ground level. That will then trigger the auger to start the process, which you will see here. So it'll start the sampling process. It goes through a automated loop in its code to go to a certain distance and then come back up. And then it'll pull all the way through the cup, and so that way it doesn't bring any soil with it. All the soil is then offloaded into the cup. The grabber will bring the cup back up and slide it back into the carousel mechanism. It will then rotate and move to its next location. There is some accuracy issues with this current system right now. There's a lot of sway in the auger. And as you can see in the current cup at the top of the inner diameter there's a lot of wear where the auger is hitting into it while the drilling process is going on. And then when it actually slides the cup back into the carousel, it doesn't get a tight fitment in there, which will lead to a lot of problems driving throughout the field.
So as Landon alluded to, there was a lot of accuracy issues. One of the larger accuracy issues is the depth control. That is a customer requirement. So we have to make sure that we're within that plus or minus 1 inch of the 24-inch interval. So currently, to initialize that height screw that motor comes up, there's limit switches. And essentially, it comes up, hits the limit switch, the drill, and then it counts the motor revolutions. There's no, other than the code counting the motor revolutions, there's really no way for it to truly detect the depth at the auger actually is. Secondly, it just goes through a pre-programmed loop. So like I said, there's no way to really detect if it's actually going into the ground, because it could be spinning and not actually penetrating the ground, which would lead to an inaccuracy. And there is no existing feedback to detect any obstacles like rocks or foreign debris if they were hit. That would obviously cause issues with our sample, and it needs to be documented. So that's something that needs to be added to the system.
Our current state for our auger design and volume control. So our sample has to be at least 24 inches deep within plus or minus 1 inch. And our current auger is only around 14 to 16 inches. And it's also only 1 inch in diameter. So it doesn't actually get the required depth or the required amount of soil, which we need at least a minimum of 16 volumetric ounces. And currently in our first testing, we got about, 3 to 4 ounces maybe with our initial cup with that 1 inch auger bit. And currently, we don't have a cleaning system for the bit. So any residue that's left on the bit could contaminate any of the other future samples. So we are going to be implementing some style of brush that gets clamped between the lid and our cup, and that will be put in place in our second semester. So.
One of the last goals of this project is for it to be an autonomous rover. Currently, it does not have that. And as you'll see in the later slides, it is driven with a homemade remote control. So what we have to do as a group is get this set up to drive wirelessly with an RC controller. And that'll work in combination with our flight controller, which we'll discuss later. The picture in the slide is just a preview of the mission planner software that we'll use to set the autonomous navigation. Then it will, once it hits these waypoints, it'll work through the soil sampling process. And the goal is for it to perform 10 soil sampling processes without human intervention. So part of to end this semester, we had to do some initial testing. We did one on the carousel and the GPS system itself. We set up a mini rover for ease to practice. This is just a preview of the mini rover driving to a single waypoint. We have the flight controller and everything set up. We put it in auto mode and it'll drive to the waypoint. And at this waypoint, there's an Arduino in the middle there that'll work through the soil sampling process.
So to allude back to Seth's deal with the Arduino communication, that's supposed to mimic our soil sampling process. So we just had an LED sequence there. So when it stopped at its waypoint, it's supposed to go over an LED set sequence, mimicking the drilling process and then go to the next waypoint.
This is our current CAD model that we have. When we originally got our CAD model, it was only an assembly file, so we didn't, no part files were included. So we basically had to break apart the entire assembly and remake basically every part. And we added in our new auger that's implemented, and we have a couple cup designs in there, and we'll have to modify our gripper design to accommodate with our new styles of cups, which will be discussed later. And then we'll also be making some changes to the carousel, but we've came a long way on the CAD model so far.
So a huge driving factor in a lot of our decision-making processes and design processes came from the NSF I-Corps program that we were involved in. And we were given the opportunity to interview over 35 plus professionals within the industry, like agronomists, electrical, software, ag, and mechanical engineers. And we got a lot of key takeaways from that. One of those, we had to prove that auger sampling was even a viable option for this instead of the traditional probe sampling. So we got a lot of feedback, and we found that it is just as effective as using a probe. And if we get precise depth control, it could be even more effective. Another thing we learned was that instead of just overlaying maps, it would be a lot more efficient to actually input ag GPS data into our mission planning software to make waypoints, and that would be much more effective and efficient. We also, through interviewing potential buyers like farmers and co-ops, we found out that it is going to require a stronger sales approach than we initially thought, and this idea isn't fully, people aren't fully grasping it yet, and we actually have to prove that this is a viable method for this to take off. And finally, we need to implement a more streamlined system along with a possible foliage removal system on the bottom of the rover to make sure any residue or foreign debris in the field is gets out of the way of our sampling area. So then we have a nice flat level surface for our cup to rest on to receive and get a precise depth accuracy.
So our first decision matrix was going back to the depth control and ground detection. That's part of where the elevator grabs the cup and it's lowering it to the ground. You couldn't really see it in the video, but there's actually a little bump switch that contacts the ground that tells the microcontroller to kick on the drill. That is not going to hold up in the environment, especially field conditions, dirt, anything like that. That little switch is going to take a lot of abuse. So we had to come up with a better solution to that. So we started with 3 criteria: cost, functionality, resource, precision, reliability across the top. We did a weighted score of 15, and we did a score from 1 to 5 across the middle, and we took that times the percentage and you add it across, and whatever weighed the highest is the winner of the decision matrix. Here we compared 3 different sensors: the FSR 402 pressure sensor. That is a piezo resistor that's a normally open circuit. As soon as you put pressure onto it, it closes. Then our INA 219 current sensor, that's a current detection module that uses a shunt resistor to detect current. And then the KW12 limit switch, which is currently being implemented. From a functionality and precision standpoint, which weighed the highest in our criteria, the INA 219 current sensor took the first place, winning essentially because of its accuracy and the ability that it does not need to be actually in the physical environment, like touching the ground like the other sensors. So it can essentially be used to detect the current spike by the microcontroller when that cup lowers, and that linear actuator that's pushing down on that table sees a current spike. It knows that it's met the resistance, and it can kick off and start the drill. And it's got a really fairly good accuracy. It's only got like 0.5 microvolts per degree Celsius offset drift. And it works through a temperature range of like -20 to 140 degrees. So
then the next decision matrix that we put together was for the auger bit. The current bit that we had was I think it was like 12 inches, so it's not even long enough for the depth of a sample they want us to get. And then we looked into the pitch of the actual auger. We did some initial testing in the field just with the regular 12-inch bits to see which ones kind of pulled up soil the best, and we found that the greater slope, the steeper it is, the better it performed. And on this matrix, we have that top bit didn't come in a long enough length that we needed, so we would needed to weld multiple of them together to get it to work. And so that's just not very optimal for going through tough soil, that you have that reliability of your weld. And then this orange one in the middle, that was from a company that actually advertises earth drilling, and this is kind of on their smaller portion. And that's the one we ended up going with because they were all similar in pricing, and it's got replaceable tips, so you can have a better cutting edge all the time. You can always have that going for you. If you go to the next slide. And then, so you can see up close pictures of the current solution compared to our optimized solution. And then we also have that brushed lid integrated with that to brush off any of the soil that's getting stuck to the actual bit.
We also have a volume control decision matrix for the cups, kind of how Josh and Cody alluded earlier to the decision matrix layout. Our criterias for our cups were based on geometry, nipple depth, soil offloading, carousel attachment, and the gripper attachment. And our 2 designs that we recently came up with for our cups is a square design and then a hexagonal design. So when that brush is in there, it's going to be less likely to spin with the rotation of the auger. And our current cup is just a PVC conglomerate, basically. It's 3-inch PVC and then a 1-inch piece of PVC, and it's kind of all glued together with a little plastic siliconed-on lid. And as you saw in the video, the auger actually ripped off the lid because that was just a snap-on lid. These will be twist-on, so we should be able to get a good force of compression on our disc brush. And our current solution, like I alluded earlier, is just a PVC, and our optimized solutions is going to be currently in our testing, we've just used PLA for our printing. In the future, we're thinking about going to polycarbonate as a more durable design. And we have both solutions that we're going to be testing, a hexagonal and a square.
just real quick, back to the cup before we get too far down. The big reason why we got to go to a square hexagon style cup is because when this is going to the ground, a current gripper, it has a half radius gripping a cup. And when we put the cleaning bit, the bit cleaner in the cup, we're want to ensure that when that drill bit comes back up through, it's going to create a torque on the cup. So we want a wrench style gripper, and this makes more sense to have the cup fit the wrench style gripper.
Yeah, so kind of like Josh said, these are the two grippers we have right now designed on CAD. We have a hexagonal one and then a square one, and we're still going through the pros and cons of each. And we have also modified our cups to have this little lip, so that way when it's pushing down to the ground, you're not like sliding down on the cup, you're pushing down on the cup. And yeah, so we have our pros and cons of these, and we're going to continue to look at those down the road.
Back to autonomy. This decision matrix was pretty easy for us. The top motor controller was provided for us. The bottom two were two that we picked out. The top one came with no documentation, no wiring schematics, nothing. We couldn't find anything on the company itself, so that one got kicked to the side pretty quickly. The two that we chose are compatible with our flight controller, and they're pretty much the same thing. The middle one is a dual channel where it runs two motors off of one motor controller, and the bottom one is a single motor controller. The reason why we chose, or the reason why the middle one won this decision matrix is because it can handle the output voltage and amperage needed to drive our rover. And these are the current solutions and optimized solutions. And as I alluded to earlier, these are our controllers. The one on the left is a homemade version. It has to be hardwired into the rover. Basically, there's no autonomy with that. And the second one is a drone RC controller. It will be implemented similar to how the mini rover platform is working right now. This is our mini rover platform. We did do a decision matrix for our flight controller. That's a Pixox 4 flight controller. That one was provided for us. So again, another easy decision matrix. We decided to stick with that. And the only real difference between the ones that we picked out with this one is just there were projects here on campus that used those flight controllers, but the sponsor wanted to stick with this one, and it saves some money when in the end on the budget.
For our first semester Gantt chart, we started out, we did the I-Core program, and then we did our SDR and PDR, and then we did some initial testing, and today we have the senior design conference.
For our second semester, we just have a lot of progress reviews, demos, and then finally bringing it to the engineering expo and dropping it off to our project sponsor. There isn't a lot of like testing or anything implemented into this because we got to see how far we end up getting before winter break. So this will be an ever evolving document as we continue to progress in this project.
This is our current budget as it stands. We are still waiting on a few things. The inner dish brush, those are going to be custom made to our specs and material. We haven't received a quote back for that, so that's why that section is blank. The 3D printing filament is for printing all the cups. Currently, we're just doing one at a time until we decide our final design. And then the RoboClaw motor controllers, the current power breakout modules, the ESCs are not going to be on the main rover. That's what we're using for initial testing on the mini rover. Those are just speed controllers. So similar to the LiPo battery, that's for the initial testing. One of the requirements needed for the main rover is to redo all the electrical, make it neater and be able to handle the environments. So we just have miscellaneous there because we haven't dug into that a whole lot. Similar with the aluminum plating and miscellaneous mechanical parts. With that larger bit, we weren't sure what we were going to have to change. We had to adjust the height of the power screw and linear rail for that height mechanism. So we just threw in some aluminum plating and miscellaneous mechanical parts until we dig further into that carousel. Any questions?
How are you measuring, when you drill down?
Yeah, so we're gonna use a combination of, that's a good question, first of all. He asked how you measure when the auger bit goes down. So we're gonna use a combination of two things, hopefully. First, we're gonna use the motor counts. So the revolutions of that power screw, but that doesn't always tell the whole story, because if that hits the ground and it's actually just spinning. So what we're actually gonna do is use the combination of that and the INA 219 current sensor. And we're gonna use basically compare and contrast them in the code to make sure that, okay, we're in a value of current range at this depth. So we're gonna go map this current out in some more testing, hopefully here before Christmas, and find our ranges that the current, the soil depth profile and how it matches the current, and also use the motor count.
So when you say motor count, that's stepper motor?
Yeah,
Yeah, okay.
So the client wants samples from range or from the top of the surface down to 24 inches?
good question. He asked, does the client want it from a range? Say one more time.
From the top of the soil down to a certain point?
Yeah.
Or could it be from 8 inches down to 24 inches?
No, good question. It has to begin at the surface soil at the top. And this is kind of not so much the engineering side, but from the agronomy side, there's two different depth profiles that agronomists look at. Your 0 to 6 range, and then your 6 inch to 24 inch range. So your 0 to 6 is your mobile nutrients, and then your non-mobile is from 6 to 24 inches. We're going to 24 inches because if we can go down to 24 inches, we can prove that and maintain depth control at that depth, we can do the 0 to 6. So.
But you said before, when if you probe versus auger.
Yep.
But a lot of times when people do soil sample, they actually do a core sample.
Yep. They can do a core sample.
By a probe.
Yeah, and they section it off. So they take what he's saying with the core sample is they take basically a tube, they shove it in the ground and it pulls up a big slug, and they section it off at the depths and then send it to the labs. With the auger, that's why true depth is super important, because you're agitating the soil. You can't mix between the 0 to 6 and that 6 to 24. So that's why for an auger to be truly valuable in a lab setting, that true depth has to be maintained.
Do you have any concerns about battery life?
We haven't dug into it a whole lot. We haven't been able to take out the main rover yet. We've been running the mini rover for a while now. The components on there, which will basically be transitioned over to the main rover. We haven't charged the battery, and we've been running it for a month now without charging it. We do have a large 48-volt battery in the rover. That's something we'll have to figure out going into the second semester once we can take it out and run some actual sampling.
That's and the battery life is something that our project sponsor told us was out of scope. He just wants us to kind of prove this idea of soil sampling, and then he's going to try and get investors to take it to the next level and explore all those other details.
Yeah, alluding to Cody's idea with the prototype. Who asked? Evan? Yeah. Did you ask a question?
That's the battery.
All right.
So you just mentioned that you want to separate the 0 to 6.
Correct.
How are you going to do that?
So for our scope, he wants to look at a range of 0 to 24. He just wants to see it. Yep, for our project scope. I was just saying, in the agronomy world, if you take this to the next prototype, you need probably more precise measuring equipment to make sure you don't overlap that interval from 0 to 6, 6 to 24. Because when this goes to the laboratory, the profile, because they're taking these nutrients and they're making a profile, and that's your variable rates of chemical seed and all this. So it's very important that it's accurate.
Can we look at your project goals at the very beginning? Yeah, it just wasn't when you initially showed that. I thought you wanted all of your sample to be from 24 inches deep plus or minus an inch. So you might want to look at rewriting that, because the sample must be obtained at 24 plus or minus 1 inch. So I thought you needed 16 ounces from between 23 and 25 inches.
Correct.
Yeah,
They're all
that's
gonna be at
not-
24 inches. We're all
But
going,
you're collecting from 0 to 20.
correct,
This is saying you're collecting from 23 to 25.
yeah,
The end goal was to go from 0 to
24 plus.
yeah.
But what this is saying is that you're
Yeah, I
getting just between.
I could
23
see,
and
I could see
25.
the confusion on that, yeah.
And so what's the volume of your cup? How much will it hold?
They're 19 ounces currently, so they have to hold at least a minimum of 16.
Have you done the calculation to see what a cylinder of 1.5 inches in diameter and 24 inches deep? What
Yeah.
volume is that?
Yeah, we ran tests on it.
How much is that?
It's like 36.
Ounces.
Yep.
So if you fill your cup, you're not getting anything from like 14 to 24. Because your cup is full. And the rest is just
Right,
going up.
Yeah, a lot of it has to do with like the speed of it too, so it's not gonna carry up like 100% of everything, it's gonna be pushing stuff out too. Cause in our initial systems testing, when we ran it, we got like 16 ounces like on the nose from that 24-inch sample. In like a really loose soil, so it's not gonna pull up like exactly 36, but we had to go up to get it to somewhere where we could at least get enough. Cause the 1-inch auger was only pulling up about 10.
You know, my concern is that you're only getting the top. The 0 to 12, 0 to 4. How do you know from where your 16 ounce is coming in that case? Because again, that cylinder is like 30 ounces.
Yeah, and I think.
Right, and that exceeds the volume of your cup.
And I think we're kind of back to the project scope of this. He wants to see it go down to 24 inches
Sure.
and maintain that accuracy. In the perfect sense, in the next prototype, there would be a larger carousel with 0 to 6 interval, and then you come back up and you go 6 to 24 interval, and another cup would come around, different cups for those different intervals.
Sure. Have you thought of doing any tests, like, creating a soil sample?
We got a soil sample bin.
But marking the different depths of soil differently so that you can tell what's in the cup at the end?
Yeah, would that would be a good test,
You do
and
like
we
that,
actually
right?
have the ability to do that with what we currently have built. Cody had built us some soil bins that are at the little over the 24-inch, 30 inches deep. So we could section that off and actually see where that actual soil from the cup is coming.
Apply it somehow, or,
Yeah,
do some type of marker to
Yeah.
see from what depth you're getting, because my concern would be you're only getting shallow.
right. Yep.
So kind of on that topic of collecting that soil up, have you looked into how it packs once it's picked up into the cup? Like, does it pack differently at a different density than is actually in the ground, or how is that going to affect the soil collection sample?
So essentially it's gonna get drawn up through the flute of the auger and pretty much ground up consistently. Unless you're in like some dense clay, that's really gonna hold up. It actually, from our initial drilling, it actually kind of, the angle of repose was pretty decent in that cup. So I don't see that being a major issue.
There's Seth, you wanna answer this one about the GPS? How you gonna determine the positions?
So the GPS is that Arduino is gonna read coordinates as it goes through and feed back to the Pixhawks. Eventually in future prototypes, they'd like it to be able to feed back to like an iPad tablet so that the user can see it. The mission planner reads the coordinates and then it communicates to the Arduino, and then the Arduino will print it out onto whatever application we decide to go with.